recording?
Yep.
Perfect. Good morning, class. How are we doing today? Good. I can't help but notice that there are considerably fewer of you than normal.
There's a test right after this.
Like directly after this one?
Yeah.
Yes.
What's the test?
Dynamics. Yeah.
I don't know. Then I found dynamics to be more fun than statics. Well, thank you very much for coming to class in the face of the dreaded dynamics midterm. It's a bi-weekly test, so this is not even a big thing. So these people who are gone have no excuse. Okay, so they're just being lazy as usual.
It's only 8%, so.
Yeah. Well, be that as it may. Good luck on the test. I hope that you do well. I hope that you studied and that there are no surprises. Anyway, might as well keep going with this class. Any questions about previous material? No? We're going to get into, perhaps not, well, actually, we could have, oh, I should have brought my dice. That's okay. I'll do the dice demonstrations next time we have class. We're going to talk about a few different topics related to arrays. I'm going to give you sort of a rough introduction to algorithms during this whole shenanigans today as well. And we're probably not going to finish this today because we got a lot to get through. But this is pertinent to upcoming assignments, so please pay attention. So anyway, we'll get to it when we get to it. We already talked about size of, so moving right along. So we've been talking about arrays. We've been talking about various utilities for arrays. One thing that we haven't talked about yet is multi-dimensional arrays. These can be extremely useful for various things. One thing that I often like to put together, one of my favorite types of problems is like board game problems. Right the guts for a game like that peg solitaire game. That was a question once on an exam. So the way that one would go about simulating a game board inside of a computer system is using a two-dimensional array to simulate a matrix of values corresponding to pieces. You could build a chess engine in the same way. So in order to declare a multi-dimensional array in C, it's very simple. You simply include multiple square braces in the declaration. You may also initialize the array using sort of nested array declarations within a larger array declaration. Because this is C, and the lines, line counts are, it doesn't really matter. A single line of code can be spread across multiple lines in the file so long as there's a semicolon at the end. If you're initializing a large matrix, my recommendation is to pop this to the next line and put each of these subarrays on a line of its own. And that way you can actually visualize it as rectangular data during initialization. If you want to declare a three-dimensional array, so a cubic data platform, then simply include 3 indices. This works in pretty much the exact same way that you might expect. If you provide X and Y here, then you will access the particular coordinates that you're after. Make sense? I'm sure you guys got enough linear algebra last year to be comfortable with the thoughts of arrays and matrices and all of that sort of thing, yeah? Hopefully. Hopefully I'm not in my 1MD3 class where not all of the class even knows what a matrix is. Incidentally, linear algebra is a mathematics of high importance if you're expecting to do computing for your career. Basically, linear algebra maps onto computing much more easily than calculus does, because this is all discrete mathematics, right? Not continuous mathematics. Because, all of this business we talked about with floating point representations should indicate that, the idea of continuous mathematics in a computer system is, somewhat ephemeral at best. So, anyway, dimensionality is indicated by the number of square braces. These are correctly thought of as arrays of arrays. Providing n minus k indexes to an n-dimensional array will produce a k-dimensional array. So, if you want to access, line 4, the array contained at the 4th index of the larger 2-dimensional array, then just provide one index, and then you can access that. Make sense? Cool. So, let's talk about strings and how they're really just character arrays. See this guy right here? That's your null character. All strings, not just in C, all strings are null terminating. There's an invisible null character at the end of every string literal. Therefore, strings will always occupy one more space in memory, one more character, than they give the appearance of. This null terminating character is extremely important, as we're going to get into. So, as it turns out, C handles strings as character arrays. Consider the following declaration. Character array bar. There's no such thing as a string data type in C. If you ask to declare a string, it will say, I don't know what that is. It's C++, I believe, has a string data type. But in C, you are dealing exclusively with character arrays. So, this foo array will be written into memory as BAR null terminating character. The recommended approach for declaring these character arrays with initial values is to not specify a size. Let the compiler figure out how big it's supposed to be, right? It will always leave itself room for the null terminating character, but you might forget to do that, right? So that's eliminating a possible source of error. If we specify a size of 10, which is of course in excess of the size of the array, we get the following. BAR null 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 null. Does anybody remember the rule for integer arrays when we initialize with fewer elements? If we initialize an array that's longer than the number of elements we're initializing it with? Yes? Nope, it fills it with zeros, right? If it's uninitialized, it's filled with garbage data, right? But if you provide an initial value, it will just write zeros in if the space is larger than the thing you're writing into that space, right? So, does anybody want to hazard a guess what the binary representation of the null character is in ASCII?
Is it all zeros?
It is all zeros. Give the man a cigar. So basically, the rules have not changed, only the data type, right? We are still backfilling with zeros. It's just that in the context of characters, a 0 means null character. Make sense? Question?
Could you make a string with numbers in it, like you wanted part 2?
Yeah, sure. You just use numeric characters rather than numbers. Right? Like, if you wanted to replace this with, quote, 423, right? It would be character 4, character 1, what did I say? 423? Sorry. 4, 2, and 3, right? But these would be represented as characters, not as numbers, right? Have you guys ever seen an Ascii table? Have I shown you an Ascii table? Okay, well let's have adventures in coding time. You guys are going to find knowing that you can look up the ordinal values of characters in an Ascii table. You are going to find that to be an extremely useful thing to know how to do. Right. So here you go. These are the characters in teal. Your decimal representations of those numbers are here in blue, and the hexadecimal representations of those numbers appear in red. You'll notice that, this table gives you only the first 128 ASCII characters. There are, of course, many more characters defined beyond these. I think at the moment it's something like 15,000 individual characters are represented using Unicode. Basically, this was the first representation of characters that really came packaged with electric typewriters. When they figured out how to wire electric typewriters into computer mainframes to provide an interface, the typewriters carried with them the manner in which they encoded characters. That's why you get some very interesting and weird characters in here, like carriage return, form feed, line feed, and bell, right? Those are all operations on a typewriter, right? If you've ever seen, in an old movie, somebody using a typewriter, it's like you have the paper at the top and the print head is printing individual letters on the paper as you type them. So it's and the paper is moving slowly to the right or the left as you're doing. I don't know if it's the right or left. It's like moving this way, I think, as you type, and then when you hit the return key, it goes ding, and it always has a bell because that's nice. That's why the return key is called the return key, by the way. It's return carriage to original position. So there's a little bit of arcane trivia for you. But at any rate, one thing that's very important to note, that your numeric characters, right, start at 48, right? So it's not like 0 is 0, 1 is 1, 2 is 2. That's not how characters work, right? When you write 423, you are actually writing 52, 50, 51 as integers, right? We're just interpreting them as characters. That's why they print as characters. Make sense? Cool. Any questions about that? Yeah. Is there anything else I wanted to say about characters? Only, I suppose, if you're using a computer to perform ordering on strings, like alphabetic ordering, something like that, it's not sorting by some sort of abstract concept of alphabetic order with respect to the actual alphabet. it is actually sorting those arrays according to their ordinal values, right? So, if you were sorting a bunch of strings according to what you thought was dictionary ordering, and one of those words starts with the question mark character, that's going to be sorted to the front of your dictionary, because it comes before all of your alphabetic characters, and like uppercase is going to appear before, like all uppercase words will appear before all lowercase words, stuff like that, right? Question?
So when you saw the ASCII code before, it was just like a line of characters and numbers. So how do we know like where the number stops? Like how do we know 115 isn't just 1 and 15?
Run that by me again?
Last time that wasn't it the ASCII thing that popped up when we found the location of it? Or was that something else?
What last thing? Is this
Like last time.
last time? Let me see what slide we're talking about.
I don't know, I think it was just like we were talking, I don't think it was a slide.
Oh,
Like something popped up that said like times 0, it was 0 times and then long string.
oh, the hexadecimal number?
Yeah.
Oh, that was a memory address. That was different.
Okay.
Yeah. Yeah, we're going to get into memory addresses when we talk about pointers, don't worry. But yeah, no, that's something else. It should be noted, though, that hexadecimal is useful because you'll notice, again, it takes maximum 3 digits to represent ASCII in decimal, but at maximum 2 digits to represent ASCII in hexadecimal. Good. All right, so now you guys know what characters are. So basically, anytime you write, single quote character, single quote, at some point the compiler is replacing that for the ordinal value, right? That's really just for our benefit. Yes?
Are the 3 dots before and after this array, is it significant?
No, that's just my indication that memory continues this way and memory continues that way. That's just like, and so on. I suppose I should have left off these verticals, but anyway. Yeah, sorry about that. Good. So, string isn't even a keyword in C. Characters may be indexed, character arrays may be indexed, just like regular arrays. String literals are always, always, always terminated by a null character. This is implicit. All strings must be null terminated, and that it's very important. Basically, any function which is derived from the C standard library is going to assume that the null terminating character exists, and it's used as a stopping condition for loops over strings, right? So, like even so far as printing a string, like %s is it's your format tag for printing a string, right? That format tag is assuming it's a null terminated string. So if it's not a null terminated string, it's going to do that array thing where it reads past the end of the array, looking for the end of the array, right, until it hits a 0. Now, zeros are reasonably frequent in garbage data, but they're not guaranteed to be in garbage data. Therefore, if you have forgotten to include enough space for the null terminating character on a string, simply printing it can result in a segfault. Right? Question?
Is it possible for you to put the non-terminated character in yourself if you didn't change anything?
Well, you don't have to put it in yourself because it's implicit, right? How C works, there is one there. Anytime you're using double quotes, there's one there, right? So you don't have to put it in explicitly. If you want to insert a null character into the middle of a word, for example, yeah, you just do \0, and that'll insert a null character. The question, I could see situations in which you might want to do that, but in general, it's best to just let the compiler handle these things. Like if you put a null terminating character into the middle of a string, if you asked to print it, it would only print up to the null character that you inserted. right? Now, if you were also scanning this thing with a pointer, looking for, like, assuming it's like a multi-string string, looking for null characters and then, like, giving that a pointer to the next character after the null character and asking printf to print that, then it would print that until it hit its null terminated character, right? So you can use this kind of stuff, right? But it's kind of a little bit of an obscure case, and it's probably best to do things simply for now, if that makes sense. Question?
So what would we have to have done wrong to eliminate the null character?
Good, excellent question. What would we have had to do wrong to eliminate the null character? Initialize this to 3 characters instead of 4, right? If you initialize this to 3 characters instead of 4, it will truncate the thing that it's trying to write into that space, rather than just overwriting it. Like, that's one case where the character array, like an array will not write it into memory that doesn't belong to it, right? So, if you only, like, basically any number here less than 4, right? If you put 2 here, it'll just write BA, no null. If you put 3, BAR, no null. And then you're in the situation where printing it is problematic. Make sense? It's reasonably trivial for situations like this where we just have a string literal that we're initializing, but sometimes you're taking input from the user and you don't necessarily know how many characters the user is going to input, right? If the user inputs more characters than you have left buffer to store those characters, you'll be in a non-null terminated string condition problem thing. Make sense? Any other questions? These are really good questions. I appreciate good questions. Makes me feel like you guys are actually interested in paying attention and stuff. So, we can receive strings directly from Scanf using the string format specifier. Notice the 14 here. We'll talk about that. By inserting this number, the 14, the format specifier may even be used to limit the number of characters that get copied into the character array. So, if, for example, you have a character array, right? You can declare it as containing 15, only read 14 from Scanf, and that way you never exceed the size of the allocated character array, and you never run into the non-null terminated string problem, right? So this is a protection, you know? The 14 does not mean that you have to read exactly 14 characters in. If you are only reading a single character in, this is still a good protection against, you know, bad things and segfaults and that sort of thing. Make sense? Good. So, okay. One thing that you may remember about Scanf, you may or may not remember it, when we're reading integers, we have to include an ampersand here. You'll notice that in this case, no ampersand has been included. We haven't quite gotten to it, but the ampersand, the purpose of it, it's a memory address operation, right? The ampersand gets you the memory address of the thing you apply the ampersand to, right? So in the case of an integer, we have to pass the address in memory that that integer is located at to Scanf because that's what it wants and expects. In the case of a character array, the word foo is itself already actually a pointer. So we don't have to give it the address because it's already an address, right? To put an ampersand here would be to give it the address of the address, which would be a problem, right? That would mean that you would actually be overwriting foo with a number which it would think it was an address. It would then try to dereference that and you would end up in invalid memory again. Alright? So, I know I'm talking a lot about pointers and we haven't talked about pointers yet, but it's really impossible to talk about C without talking about pointers. And I don't think it's wrong to give you that impression this early in the course. So, good. Wonderful. A common form of security vulnerability in C and C++ programs is array overflow. I've already sort of done this demonstration, so I'll zip through this. Arrays are replaced with pointer arithmetic by the compiler with no bounds checking. If you tell C to write 100 characters into a 50-character array, it will happily do so. The extra 50 characters will be written into the memory that comes after the character array. This can overwrite all kinds of useful things, like other variables, and if the character array is stored in the stack, function call information can also be vulnerable. The moral of the story is that you should always limit the things you write into an array to the size of the array manually. In C programming, this is your responsibility, not the language's responsibility. That's one of the things that makes C, this is one of the reasons I said at the beginning of the course, it's time to put away our children's toys in Python and learn a real language. A language that doesn't treat you like a child. So, this is kind of this is a different way of arriving at the same stack smash error that we had previously. So if we have a query which, contains only 10 characters, and then we ask the user to populate this query and do not protect the size of the string that we're reading in, if the user enters something like, just a bunch of J's, in excess of 10 J's, shall we say, it will output this, this series of J's and then terminate on a stack smashing attack. Make sense? Any questions? Yes?
Why would it not detect it before printing it?
Probably because it's happening on the read operation rather than the write operation. Yeah. So, and now for something completely different. This is like my favorite comic. All right? This is my favorite comic with respect to computers and stuff. So, if you'll indulge me, I'm going to read it to you. I don't get many opportunities to use my caveman voice.
Who can explain frog sort algorithm? Start with empty list. For each integer, put that number dead flies in one box. Then put frog in each box. When frog leave box, append that box's fly number to list. More fly take longer to eat. When all frogs gone from boxes, list order. What is maximum step number? Log frog boxes. Very good. Homework is program frog sort on home frog computer. Later. Bah, me understand, but keep getting off by frog error.
This will be more funny once we've studied these algorithms, but again, that's my favorite comic. So, thank you for indulging me. So, so we're going to, I'm basically assuming at this point that you know everything you need to know to, do the assignment and stuff. Aside from going through some of the algorithms that I'm asking you to produce on that assignment. So that's the purpose now. If we don't quite get through all of them before the assignment, I forget if the assignment is due. It's due the week after reading week, right? I didn't make it due the end of reading week. That's just cruel. Did I? That might be a bit cruel. I'll take a look. Somebody send me an email. I'll take a look at the schedule. See if we can't, Anyway, so there might be an extension on that. I'm going to take a look at the calendar, see if we can squeeze it in there. But Anyway, so sorting algorithms. It turns out that the difference between a good algorithm and a bad algorithm can be whether you or not you can effectively compute the thing you're attempting to compute, right? I showed you guys that chart of the different runtimes recently, did I? Yeah, I did. So, so algorithms research is an entire subdiscipline of computer science. It's one of the ones that's possibly most important to like the development of like the modern information age, or perhaps the postmodern information age, depending on how you want to look at things. The only reason something like Twitter, Facebook, or Google works is because we have developed better algorithms over time. One of the classic algorithms, which is often, sorting algorithms are often used as your like intro to how algorithms are developed and researched, right? Sorting algorithms are extremely important to computing. Back in the 70s, it was considered common knowledge, or perhaps common wisdom, that 30% of all computing cycles were spent sorting. And if that's not true these days, it's not because sorting is less important, it's because we have better algorithms now and we don't have to spend that as much time doing it, right? So, the first formal analyses of sorting algorithms began in the 1950s. Many are necessary because there is no quote-unquote best algorithm. All sorting algorithms are better for different purposes, right? Man, I wish I brought my dice. That's okay, we'll do it after the break. Okay. Here's a hint, all right? The three algorithms, bubble sort, insertion sort, and shell sort, that I'm going to be talking about, I've already done dice demonstrations for them, of those algorithms for my 2CO3 class. So if you look up my YouTube videos for those classes, you can see the dice demonstration. I apologize for not bringing my dice today, but we'll get there. I don't have time to run back to my office. But anyway, so there's no best sorting algorithm. Each sorting algorithm has better or worse performance depending on the situation you're in. Because you guys are mechatronics students, we're going to focus on sorting algorithms that are good for small embedded system applications, right? Yes. So these conditions that affect runtime can be how sorted your list is to begin with. We're going to call that degree of disorder. Whether you optimize for runtime, memory, or call stack usage. Despite the venerable status of sorting algorithms research, advances are still being made, relatively recently as well. Python's standard sorting algorithm is called TimSort, named after a bloke named Tim. It uses ordered subsequences to improve performance. And we also have library sort, which allocates extra memory to gaps, which allow the insertion of entries without reorganization of the entire array. Arguably, the best general purpose sorting algorithm is quicksort. It's a recursive algorithm that you guys don't have enough algorithms under your belt or recursion under your belt to probably have a true appreciation for the genius of quicksort, but we'll start off from the beginning. What is a sorting algorithm? How is it defined? A sorting algorithm is used to rearrange the elements of an array or a list or any sort of linear data structure such that the elements are in order. In terms of numeric values, in order means normally from lowest to highest. However, depending on your application, the concept of ordering might have different meanings. For example, if you're trying to sort records in a database, you will often want to sort them by date rather than by raw integer numbers, right? So the means of comparison will differ depending on your application. Integer comparison and like natural numbers, this is what we use for a teaching tool, but you're expected to be able to generalize this to other types of situations, right? Make sense? Good. Like you can like make these a lot more complicated, make them like records, like medical records in a database or tweets in a database and all kinds of stuff, right? Make sense? Good. So, the input to a sorting algorithm is an array of values of arbitrary size, and the output is an array of values of the same size in which the values are in ascending order. Basically, to get a descending sort, all you have to do is swap a less than for a greater than, and it's the same bloody algorithm to a T. Make sense? So, let's talk about bubble sort. Bubble sort is probably the easiest sorting algorithm to understand. I don't know. It's kind of, I'd say, it's in a tie for the prestigious place of most basic bitch sorting algorithm. Selection sort is the other one. But anyway, so bubble sort's basic operation is to examine two numbers and swap them if they are in the wrong order. We go through the array, making many examinations, and by the time we hit the end, by the time we've performed all of our examinations, the array is guaranteed to be sorted. So, after one pass through the array, the item at the end of the array is guaranteed to be in the right place, so the next pass can safely ignore it. Bubble sort will make n-1 passes, given an array of size n. By the n-1th pass, the whole array is guaranteed to be sorted. So, this is bubble sort. We're starting here, all right? So we have this array, which is not ordered. The two numbers in blue are the numbers which are currently under examination, right? So we examine this first pair. Notice that 9 is greater than 4. Swap them, right? Examine the next pair. Swap, 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 and there's 9. You'll notice that we actually, in this case, started with a number that was supposed to go at the end. The green numbers here indicate numbers which are in the sorted section of the array. Let me just blow this up a little bit, eh? Oh, not that much. A little bit better? There we go. That's better. So, that's the first pass. Next pass occurs in exactly the same manner. We just skip this last examination because one of these guys is guaranteed sorted, right? So examine, in this case, these are in the correct order, so we do not swap. Swap, don't swap, swap, swap. 7 goes to the end, right? Next pass. Swap, don't swap, swap, swap. The other 7 is brought to the back. So this is why it's called bubble sort. Although some people don't like the bubble analogy because if you think of numbers as being heavier, you've got the heavy things rising to the top, which is the opposite of how bubbles work, right? But if you think about it maybe the size of the number is like the size of the bubble, then the analogy works better. But anyway, if you look at, if you sort of step back from this algorithm and squint at it, you can see that the larger numbers are gradually bubbling up to the top as we make our passes, right? That's where the name bubble sort comes from. Make sense? Cool. This is a good algorithm to never ever use because it's terrible. It is good to understand though, because it does rather well illustrate what our object is here with sorting. So, the number of swap operations we required in the previous example was 13. The total number of examinations is 21 for an array of size 7. Basically, the object of algorithms research is to reduce these two numbers, right? Number of examinations and number of swaps. We want to get that as low as possible. The number of times we have to do something in order to, perform the algorithm, the longer it takes. The longer it takes, the less we can process in a fixed amount of time, right? So, for each additional element in the array, we add n-1 to the total number of examinations. This means that the total number of operations is proportional to the square of the size of the array, right? Does that make sense? The total number of operations we have to perform is proportional to the square of the size of the array, right? The way that we say this, when we're talking more rigorously about algorithms, is we say that this algorithm is big O n squared, or the order of growth of this algorithm it's proportional to the square of n, right? We're interested in proportionality, not finding the actual direct, amount of, we can't predict the amount of time that the algorithm will actually take because it's dependent on a large number of things, It's dependent on what operating system you're using, what other software you're running on the operating system, what the weather's like that day, whether your laptop's in power saving mode. All of these things affect algorithm runtime. It is the definition of madness to try to account for all of those variables. So, what we do, we just want a kind of a rough classification of how this algorithm performs in comparison to other algorithms, right? That's why we're concerned with the proportionality rather than trying to directly derive a function for how long it's going to take. Make sense? There are too many variables. So, bubble sort can't tell the number of swaps that are needed before it makes a pass. So it's not an adaptive algorithm. The same number of examinations will occur regardless of the orderedness of the array. Therefore, we say that the best case runtime is equal to the worst case runtime. Or at least it's proportional to the worst case runtime. Make sense? That's why bubble sort is such a basic bitch. It does not use any information about the orderedness of the array in order to optimize itself. It just stupidly goes through every number one by one, swapping them as necessary, right? Advantage of bubble sort though, the program size is very small. So if you're on a very, very, very memory limited system, and you are actually concerned about how many instructions your program composes, bubble sort is a good one. Though still not as good as shell sort, as we're going to see. So, let's talk about big O notation. The mathematical analysis of the performance characteristics of algorithms is an entire subdiscipline of research within software engineering and computer science. It is quite difficult to measure software runtime. Different computers will have different runtimes. The same computer with different operating systems will have different runtimes. Linux is best. Something like a comprehensive survey of all computer systems is impractical. Can you even imagine? Right? Can you imagine being the researcher that has to figure out how quick bubble sort works on a Fitbit? Right? So, the algorithms community has made some decisions about what is important and what is unimportant with respect to measuring algorithmic efficiency. Generally speaking, the time it takes a system to execute an instruction is unimportant, compared to how quickly the runtime grows with respect to the size of the input. right? We're not concerned with how fast your computer executes any single instruction. We're concerned with how fast that grows when you add more inputs. So what do we mean by this size of the input nonsense? Generally, this refers to the size of the data structure that the algorithm is applied to. So the size of the array. How many items are we sorting? In the case of bubble sort, the size of the input is the number of items that are in the array to be sorted. In general, the relation of the input to the runtime can be expressed by a mathematical expression. Consider the following expression. an squared plus bn plus c. At small levels, at small numbers n, like n is less than 10, there's, you can't discount the contribution of the bn component or even the c component, right? However, as n grows, the magnitude of this equation is going to become overwhelmingly dominated by the n squared term, right? Like, it doesn't matter how big these a, b, and c constants are, n can always outpace them, right? Even if c is 10,000, all it would take is n being 10,000, and c is minuscule in comparison to 10,000 squared, right? That's why, when we are deciding what the big O representation of an equation like this is, we are only concerned with the highest power. We are only concerned with that term in the equation which overwhelmingly dominates the output at high levels of n. So, yes, I kind of just already said this slide, but yes. For large values of n, the runtime will be mostly, even overwhelmingly, determined by the term with the highest power of n. We also don't care about the constants a, b, and c. This is where the individual differences between computer systems will show up. The constants are also affected by the specifics of algorithm implementation. Reducing these constant terms is also an active and important area of research, but it does not affect the overall proportionality of the algorithm. In terms of bubble sort, power of n is how many times you have to examine or swap. The constant term is how long it takes you to perform each examine or swap. So essentially, just one final word. This is a nested loop, right? This is a loop. This is a loop. We're performing some operation n squared times because these loops operate proportionally to the number of n's you have. That's why it's big O n squared. Any questions? Thank you. Get out of here.